So in this video, we'll be looking at limit at infinity and asymptotes. Okay, so far we've been looking at how the first and the second derivatives affect the shape of a graph. For example, we use the first derivative to determine which interval the function is increasing or decreasing, and then we also use the second derivative to determine the concavity, whether it's concave up or concave down within an interval. So if we want to know the shape of a graph on an unbounded interval, unbounded interval means from negative infinity to positive infinity, then we need to know the behavior of such a function as the independent variable approaches both positive infinity and negative infinity. And so we look at limits of a function at infinities. All right, now if you recall, okay, we have limit as x approaches a of f of x is equal to m, means that as x approaches a, all right, f of x approaches m. So as x approaches a, f of x goes to m, capital M. All right. So we can extend the same idea to infinities as well. So for example, if I have the limit, if I have a function, let's start with functions. If I have a function f of x is equal to 3 plus 1 over x, then the limit as x approaches infinity of f of x is the same as the limit as x approaches infinity of 3 plus 1 over x, because this whole function is what f of x is. So the limit of a function means wherever we see x, we replace that with infinity. So this is equal to 3 plus 1 over infinity, which is equal to 3 plus 0, which is equal to 3. We also look at how this function behaves as it approaches negative infinity as well. So this implies that as x grows larger and larger to infinity, f of x goes to 3. All right, so we look at the limit as x approaches negative infinity of f of x, and this is equal to the limit as x approaches negative infinity of 3 plus 1 over x, which is equal to 3 plus 1 over negative infinity, which is equal to 3 minus 1 over infinity, 3 minus 0, which is equal to 3. What this means is that as x grows to negative infinity, f of x goes to positive 3. So you notice that for the same function f of x, which is equal to 3 plus 1 over x, as x goes to both positive and negative infinity, the function goes to positive 3. All right, so the function approaches the asymptote. You call this the asymptote. All right, asymptote f of x, which is equal to 3. Now we use f of x to be y, so y is equal to 3. So the asymptote, so the function approaches the asymptote y is equal to 3 as x approaches both positive and negative infinity. And since this is a horizontal line, we say that this is the horizontal asymptote. So more generally speaking, if the limit as x approaches both positive and negative infinity of f of x is equal to m, then what this means is that the graph of f of x approaches the line y is equal to m. All right, and in this case, the line y is equal to m is known as the horizontal asymptote of the function f of x. Okay, now let's look at another example. if I have f of x is equal to 1 over x squared, okay, then the behavior of such a function as it approaches as x approaches both negative and positive infinity is, we first of all test for the positive infinity. You can also start with negative infinity, it doesn't matter which one you start with, of f of x is equal to the limit as x approaches infinity of 1 over x squared, and this is equal to 1 over infinity squared, which is equal to 0. Then we test for when x approaches negative infinity of f of x, and this is equal to the limit as x approaches negative infinity of 1 over x squared, and this is also equal to 0. So since f of x is approaching 0 as x goes to negative infinity and positive infinity, it means that the line y is equal to 0 is the horizontal asymptote, forgive me for my handwriting, of the function f of x is equal to 1 over x squared. All right, so what this means is, let's take note, if the limit as x approaches positive infinity of f of x is equal to m, or the limit as x approaches negative infinity of f of x is equal to m, then we say that the line y is equal to m is a horizontal asymptote of f of x. Okay, let's look at another example. If I have f of x is equal to 7 minus 3 over x. To find the horizontal asymptote of this function, we find the limit of the function as the independent variable approaches both positive and negative infinity. All right, so we have limit as x approaches infinity of f of x. This is equal to the limit as x approaches infinity of 7 minus 3 over x, and this is equal to 7 minus 3 over infinity, which is 7 minus 0, which is equal to 7. All right, then we look at the behavior as approaches negative infinity of f of x, and this is equal to the limit as x approaches negative infinity of 7 minus 3 over negative infinity, which is equal to 7 minus negative 0, which is 7 plus 0, which is equal to 7. So since the limit as x approaches both plus or minus infinity of f of x is equal to 7, it implies that f of x, all right, has a horizontal asymptote of y is equal to 7. All right, then another example is if I have f of x is equal to 5 plus 3 over x. I'm sure from now on you'll be able to, from what we have discussed so far, you'll be able to determine the horizontal asymptote of this function. So we find the limit as x approaches infinity of f of x. This is equal to the limit as x approaches infinity of 5 plus 3 over x. This is equal to 5 plus 3 over infinity. This is equal to 5 plus 0, which is equal to 5. Then we find the limit as x approaches minus infinity of f of x, and this is equal to the limit as x approaches infinity of 5 plus 3 over minus infinity. This is equal to 5 minus 0, which is equal to 5. So since the limit as x approaches plus or minus infinity of f of x is equal to 5, it implies that the line y is equal to 5 is the horizontal asymptote of the function f of x is equal to 5 plus 3 over x. All right, now we look at the end behavior of rational functions. All right, a rational function is a function of the form f of x is equal to p of x over q of x, where both p of x and q of x are polynomials. All right, so the limit at infinity of a rational function depends on the relationship between the degree of p of x and q of x. Now, to evaluate the limit at infinity of f of x, all right, we need to divide both p of x and q of x by the highest exponent of x in the denominator q of x. This determines which term in f of x dominates the behavior of the function at large values of x. All right, so for example, if I have f of x is equal to 4x plus 1 divided by 3x minus 2, then if I want to determine the horizontal asymptote, we find the limit as x approaches both positive and negative infinity of 4x plus 1 over 3x minus 2. If I'm to find the limit of a rational function where both numerator and denominator are polynomials, all right, and the limit is approaching plus or negative infinity, we divide both the numerator, each term, and the denominator, each term, by the highest power in the denominator. All right, so since the highest x power in the denominator, highest degree in the denominator is x, it means we divide both. We have limit as x approaches plus or minus infinity of 4x plus 1 divided by 3x minus 2. All right, highest degree in here is x. All right, highest degree is 1, so we divide here by x, divide here by x, divide here by x, divide here by x as well. This only happens when the limit is approaching both positive and negative infinity. So this is limit as x approaches plus or minus infinity 4 plus 1 over x divided by 3 minus 2 over x. Now we can substitute our limit in there, so we have 4. This will be plus or minus 1 over x, 1 over infinity divided by 3 minus or plus 2 over infinity. And this is equal to 4 plus or minus 0 divided by 3 minus or plus 0, which is equal to 4 over 3. All right, so since the limit as x approaches plus or minus infinity of 4x plus 1 divided by 3x minus 2 is equal to 4 over 3, it implies that 4x plus 1 over 3x minus 2 has a horizontal asymptote of the line represented by the line y is equal to 4 over 3. Okay, let's look at another example. If I have f of x is equal to x squared plus 3x divided by 2x cubed plus 7x squared plus 7x plus 2, okay, and I want to determine the horizontal asymptote, then it means we're looking at the behavior of the function at negative infinity and positive infinity, right? So this is x squared plus 3x all over 2x squared, 2x cubed plus 7x squared plus 7x plus 2, right? So to simplify this, we divide each term by the highest, the leading term of the denominator, and the leading term is 2x cubed. So we divide here by x cubed, x cubed, x cubed, x cubed, x cubed, and here by x cubed. So this is limit as x approaches plus or minus infinity of 1 over x plus 3 over x squared all over 2 plus 7 over x plus 7 over x squared plus 2 over s cubed. Alright, so this becomes 1 over infinity plus or minus 3 over infinity all over, we have 2 plus or minus 7 over infinity plus or minus 7 over infinity plus or minus 2 over infinity. And this is equal to 0 minus 0 over 2, which is equal to 0 over 2, which is equal to 0. So since the limit as x approaches plus or minus infinity of f of x is equal to 0, it implies that x squared plus 3x all over 2x cubed plus 7x squared plus 7x plus 2 has a horizontal asymptote represented by the line y is equal to 0. All right. Another example, if we have f of x given by 5x squared plus 2x all over 2x plus 3. Now, since the degree of the denominator is less than the numerator, we perform long division. All right, so we divide the numerator by the denominator, and that will give us 5x over 2 minus 13 over 4, remainder 39 over 4, all divided by the divisor, which is 2x plus 3. Please pause the video and then perform the long division. All right, so this here is the quotient, and this here, this is the remainder, and this is the divisor. All right, so if I have f of x, which is equal to p of x divided by q of x, then this is equal to the quotient, which is the answer that we'll get, plus the remainder divided by the divisor. All right, so we have f of x, which is equal to the 5x squared plus 2x divided by 2x plus 3. This is the same as 5 over 2x minus 13 over 4, all right, plus 39 over 4 divided by 2x plus 3. All right, now I'll perform some operations. We take this quotient to the other side of the equality sign. All right, so I'll have f of x minus 5x over 2 minus 13 over 4. This is equal to 39 over 4 divided by 2x plus 3. And so if I'm to find the limit as x approaches both positive infinity and negative infinity on the left hand side, I have to perform the same thing on the right hand side. Right, so limit as x approaches positive and negative infinity of f of x minus, we have 5x over 2 minus 13 over 4. This is the same as the limit as x approaches both positive and negative infinity of 39 over 4 divided by 2x plus 3. Okay, so here this is equal to, limit means wherever we see x, we put the plus or minus infinity there. Okay, so this becomes 39 over 4 divided by infinity plus 3, which is equal to 39 over 4 divided by infinity, which is equal to 0. So limit as x approaches plus or minus infinity of f of x minus 5x over 2 minus 13 over 4 is equal to 0. This means that the graph f of x, all right, approaches f of x approaches 5x over 2 minus 13 over 4 as x approaches both positive and negative infinity. This is known as oblique asymptote. So, if the degree of the numerator is more than the degree of the denominator, all right, if you are given f of x is equal to p of x divided by k of x, if the degree of the numerator is greater than the degree of the denominator, then f of x, which is equal to p of x over k of x, is equal to some function g of x plus r of x, which is the remainder, divided by the divisor, which is still q of x. All right, so at the end we have f of x is equal to g of x plus r of x, all divided by q of x. Okay, now we can take the g of x to this side, so we have f of x minus g of x is equal to r of x all over q of x. All right, so if we find a limit on both sides, we'll have limit as x approaches both positive and negative infinity of f of x minus g of x is equal to the limit as x approaches both positive and negative infinity of r of x divided by q of x. Now, since the degree of r of x is less than the degree of q of x, it will automatically mean that the limit as x approaches positive and negative infinity of r of x divided by q of x is equal to 0. If that is the case, then that implies that the limit as x approaches positive and negative infinity of f of x minus g of x, which was equal to the limit as x approaches negative and positive infinity of r of x over q of x, is equal to 0. If the degree of p of x is exactly 1 more than the degree of q of x, then g of x is linear, and we call g of x an oblique asymptote. All right, so if the degree of p of x is exactly 1 more than the degree of q of x, then g of x is linear, and g of x is called an oblique asymptote. All right, so let's look at another example. If I have f of x is equal to x squared minus x minus 6 divided by x plus 3, since the degree of the numerator is higher than the degree of the denominator, we can divide both sides, all right, through by. So we have limit as x approaches positive and negative infinity of f of x, all right. This is equal to the limit as x approaches negative and positive infinity of x squared minus x minus 6 all over x plus 3. So if we divide these, x squared minus x minus 6 over x plus 3, this is the same as x minus 4 quotient plus remainder 6 divided by the divisor x plus 3. So at the end of the day, we have f of x being equal to x minus 4 plus 6 over x plus 3. All right, so we take the quotient to this side, so we have f of x minus x minus 4. This is equal to 6 over x plus 3. And so the limit as x approaches positive or negative infinity of f of x minus x minus 4 is equal to the limit as x approaches negative and positive infinity of 6 over x plus 3. This is equal to 6 over infinity, which is equal to 0. All right, so that means limit as x approaches positive and negative infinity of f of x minus 4, this is equal to 0. This implies that the line y is equal to x minus 4 is an oblique asymptote of the graph f of x is equal to x squared minus x minus 6 all over x plus 3. All right.